Give an example of sets A and B for which the union of A is equal to the union of B, but A is not equal to B. There's another pretty straightforward question, just trying to test your understanding of what the unions of sets are. So let's get through it. Specifically, we want to know how this thing behaves. This big U operator acts on a set. So recall that UA, or the union of A, is defined as set of X such that X is in some element of A. So if A is equal to something like 1, 2, 3, then UA is equal to, well, any element that is inside some element of A. So 1 is inside an element of A, 1 is inside this bigger element, 2 is inside this bigger element, and 3 is inside this bigger element, right? So the union of A is going to be 1, 2, 3. That's pretty simple, right? Now the question is the union operator unique? Does it always produce a unique answer? Or like, if you know the union operator or the union of a set, does that mean that you can go back and find the set itself? Turns out this is not true, and this is what the exercise is trying to show us. So what we want is, now that we have the set A and its corresponding UA, we want some UB, we want some B. I'm going to write this down. Some B such that UB is equal to UA, and of course, this is just 1, 2, 3, but B is different from A. Now, there's several ways to go about this. I think that the main insight is that these 3 elements, 1, 2, and 3, that we had here on our set A were just split up arbitrarily, and we can split them up in any other way we want. So what I did to solve this problem is, let's say B is a different way that we can split up these elements into smaller sets. So why don't we split them up into even and odd, for instance. So let B be the set containing the set 1, comma 3, and also containing the set 2, right? Then what is UB? That's our question. So UB is X such that X is in some element of B. And I forgot to write this earlier, but if you want to see it in a more mathematical notation, in a much more rigorous language, then you can write this as X such that there exists some little b in big B such that X is in little b. And just to go back to our previous example, see that I'm explaining this properly. Let's say, I'm going to move this down just for a minute. Well, the same definition applies to everything. So just let's extend this and say that X such that there exists some little a in big A such that X is in little a, right? Okay, so what are these little a's? I'm going to say that this is A1, this is A2, and this is A3. So UA is equal to any X such that X is in any one of these little a's. And so you'll find that, actually I don't have to write it again. You'll find that 1 is in little a1, 2 is in little a2, and 3 is in little a3. And that's how I constructed UA. If you want to do it more rigorously, which is always good. It's always good to be rigorous. Okay, cool. Now going back to our example. UB is equal to x such that x is in some element of B, or more rigorously, x such that there exists some little b in big B such that x is in little b. So let's decompose big B into little b's. So let's call this one B1 and B2. So B is equal to B1, B2. Right? Hope this is not too confusing so far. And then what do we want? We want every x contained within one of these little b's. So UB is equal to whatever's in B1, so 1, 3, and then whatever's in B2, so 2. Now, is it true? A natural question to ask now, is it true that UB is equal to UA? And the answer is, of course, yes. Because by the very first axiom, the axiom of extensionality, I'm not going to write the whole full definition, but two sets A and B are equal if they contain the same elements. Okay, so UA is equal to 1, 2, 3, and UB is equal to 1, 3, 2. And up to rearrangement, these things contain exactly the same elements. So UA is equal to UB. But is it true that A is different from B? Well, you'll find that A is the set containing 2, 3. B is equal to the set containing 1, 3, and 2. And 1 second. Oops. And how do we check that they're equal or unequal? To show that they're not equal, we just have to show that one of the elements in A is not an element of B, or vice versa, that one of the elements of B is not an element of A. And a simple way to show that is to ask the question, is 1, 3 in A? And no. 1, 3 is neither this element, nor this element, nor this element. So, indeed, A is not equal to B. Thus, we have shown the moral of the story that UA equal to UB does not imply big pink does not imply that A equals B. All right. Or if you want to do it in Anderton's notation, then you use the negation operator. So I should probably start doing that so you get used to this sort of notation. Yeah. So we have shown that it is not true that UA equals UB implies that A equals B. All right, cool. That's all for this exercise. I'll see you in the next video.